nature of rational numbers. They can be represented in form of a fraction where I can write any rational number in the form of p by q. So if you look at random questions, or if you have some numbers like 3/8, and now you want to find the decimal expansion of it, how would you do that? You have to go and use your basics, okay? The one that you have been studying in your previous classes. What you would do is, because 8 is your divisor here, you want to divide the top number and then find out the answer for that. So 8 divides 3. I'll just go ahead and do it. It is something I'm doing to just recap how we used to do it. Now 8 divides 3, obviously it's not divisible, so I'll write 8 times 0 is 0, and then bring down that 3. I'll put a decimal on my answer side and then make it 30. 8 times how much is nearest to 30? 8 times 3 is 24, so I'm going to write 24 here. Again, remove 24 from 30, gives you 6. So another 0 we can add. We will keep on adding zeros unless and until we get the remainder 0, or what? We will definitely have a look at many examples first. So this is the first one I'm taking. I got 6 as the remainder, so I'm writing 60. 8 times how much is nearest to 60? 8 times 7 is 56. Now removing 56 from 60 gives me 4 as the remainder. I am allowed to bring as many zeros as possible, but always bring one zero at a time. So 8 times 5 is 40. I'm very lucky with this because my decimal has now terminated, or what I got is a fixed answer, 0.375. Now because you get the remainder 0, this kind of decimal expansion is called terminating decimal. So every terminating decimal is a rational number, okay? Terminating decimal. But it's not every time that you get the remainder 0, do you? No, you don't get the 0 remainder every time. So let's take an example of other kind of division where you get something else. So let's say, for example, I want you to divide 10 by 3. I'm sure you're quite familiar with this kind of division. So you do 10 divided by 3 gives you 3 times 3 is 9, gives you a remainder of 1. And because I'm getting a remainder, I'm allowed to put a decimal and follow by 1 0 at a time. And now again I get the same number 10. 3 times 3 is 9, again gets me the same remainder 1 0. So I'll keep on doing it. There is no way I would ever terminate this division, or I don't think, or what I don't think, no, it's 100% sure that every time you're going to get the same remainder 1, and because the remainder is same, there is no way you can actually terminate this division method, okay? You have to continue the process. So such kind of division, or such kind of decimal value is now called non-terminating, because it's never going to give you a remainder 0, okay? Non-terminating, but something is so special here. You get the same value over and over again. After the decimal, whatever value you're getting, it does not change. You're getting the same value again and again and again. So non-terminating, this kind of expansion or this kind of repetition is now called as recurring, okay? Non-terminating, recurring or repeating, you can use either of the word. This is the second kind of rational number, non-terminating, recurring decimal or repeating decimal. Either way, it means the same thing. All right, I hope this is making sense. And obviously the other way we write this decimal expansion would be now as 3.3333. The repeating number is now kept upon a bar like this, okay? Now it's not that every time there is only one digit that is going to repeat. There are many examples, like let me take 1 divided by 7. Let's divide 1 by 7. Let's see at what point do we get the repeating digits, or if this is ever going to terminate or not. Let's check it out. So I'm going to do the same thing. 7 divides 1. So 7 times 0 is 0, giving me a decimal on my answer, and I'm allowed to make this as 10. Now 7 times 1 is 7, gives me the remainder 3. Now again, because of the decimal that I have introduced on my answer side, I am allowed to put 0, 1 at a time. So 7 times how much is nearest to 30? 7 times 4 is 28. And then remainder here is 2. And now I'll get 20, okay, by getting another 0. 7 times how much is nearest to 20? 7 times 2 is 14, gives me the remainder 6. 60. That's the next number. You see my remainder at every point is coming different. So there is no way I would see any repetition. 7 times how much is nearest to 60? 7 times 8 is 56, giving me the remainder 4. Again, I'll make it as 40 by introducing 0. 7 times 5 is 35. Removing 35 from 40 gives me 5. Now 50. Yeah? 7 times how much is nearest to 50? 7 times 7 is 49. And now gives me the remainder 1. Now 1 as in 10. So 7 times how much is 10? 7 times 1 is 7. 8, 9, 10. Again a remainder of 3. So 30, if you'll see, then you did get the remainder 1 before, or in the first place itself, you had got the remainder of 1, which means the next thing that's going to happen is you're going to get a remainder of 1, followed by 3, followed by 2, followed by 6, and this will carry on, okay? So 7 times how much is nearest to 30? 7 times 4. So now you see, you have these digits repeating, and this is exactly the same thing that will repeat, which means 1 out of 7, if I have to write it otherwise, then it will be written as 0.142857, and after that it started repeating. So I'll just put the entire bar upon the digits that will now repeat. So you see, 1 by 7 is also an example of terminating, non-terminating, repeating decimal. Okay, though we have how many digits repeating? 6 digits repeating. Okay, similarly, if you go on and try with big numbers like prime numbers especially, then you'll get larger set of digits that will repeat as a block. Okay, so this is how you find out whether something is terminating or non-terminating, by regular division. Now, the best part is, if you ever have a number in this form, okay, then how can we get back into this fractional form? Because right now we understood that if digits are repeating in a decimal expansion, that is still a rational number. And by the definition of rational number, I know that every rational number can be represented as a fraction, P upon Q. So if I'll ask you, if 0.33333 is given to you, then what exactly can you write it as a fraction? Or maybe if I'll give you 1.7777, yeah? These are examples of rational, but how can I actually get back into this fractional form? How to do that? Okay, that is the main part of this topic, and in fact this lesson is mainly to make you understand how exactly can you solve these kind of non-terminating repeating decimals into a fraction. That is the main thing we will study in today's session. Not only one digit repeats, like in the example that I showed you, there could be a block of digits repeating. And not only that, sometimes there are cases when you have one of the digits not repeating while the next group, or just 3, 2, 3, 2. Look at this example. You see, this one particularly is not repeating, only this part 3, 2 is repeating. There are examples of numbers like this. So what is the method of getting these non-repeating decimals to not non-repeating, non-terminating repeating decimals? How exactly can we get them into a fraction? That is what we will learn. So let's try with one of the interesting numbers that you must have seen. So like for example 0.999999 and so on. This is a question from your book, exercise 1.3, and I want you to understand how exactly can you convert a decimal like this into a fraction. Okay, first of all, you will say that this question will tell you write this in the form of p by q. Okay, they'll tell you to write it in the form of, express it in the form of p by q. So what we'll do is we'll not write two variables like this. We'll say it is equal to some unknown thing. I don't know what that unknown fraction is. So I'll say let x equals to 0.99999 and so on. Okay. Now what do we take care of is we look at the digit repeating. How many digits are repeating here? I clearly see there is one digit repeating. Yeah, 9 itself is repeating or recurring. So when you have one digit being repeated, then what you'll do is you'll multiply 10, because upon multiplying this equation by 10, what happens if I'll multiply by 10 is my left side becomes x times 10, 10x, okay, and my right side becomes 9.9999, and I just get the same thing as I had before. The only difference is I have something at the front. In front of the decimal 2, I have a number now, unlike before. Now, the best part is what you got here as 9.99999, you can split that into two parts, okay? You can split this into two parts. You can say that this is a result of adding that number 9 to 0.99999, which is what we represented by x in the first case, yeah? So I'm going to say that this 10x is equal to 9 plus 0.999. I just removed that repeated part. Now, from the first equation that I have considered here, I can say that this 0.99999 is nothing but x, because that is what I started with. I'm saying that this is x, so 10x should be equal to 9 plus x. Okay, now you see, it's like solving equation in one variable. You have done this in class 8. Yeah, you have one variable, both sides, so you have to bring them together and then solve it. So you have this smaller x value this side. I'm going to take it to the other side, and I think you know that if you are moving terms from one side to another, then you have to oppose the operation, meaning this x is getting added this side, so I must take it to the other side and subtract. So if I'll take it to the other side, it becomes 10x minus x, yeah, equals to 9. So 9x, 10x minus 1x is 9x, equals to 9. So x equals to 9 divided by 9. What is that? 1. So that is the reason why I think it makes sense to you that 0.99999 is always equivalent to 1. This is what the interesting part is. Okay, this is interesting because you must have seen 0.99999 as a fraction. What you can actually write it, it is actually equal to 1. That's interesting. Let's take some more examples of this so that you don't have to worry about converting these kind of recurring decimals to fractions anymore. Okay, so I want you to be fully confident after this session. Let's take more examples. If I'll take 0.333333. So where do we get this kind of recurring decimal? If I'll go back and show you, we got this when I divided So yeah, 3.33, that we got it as 3.33 here. I'm taking the example of 0.333. So I'll say first of all that this y, any variable, is equal to 0.33333. Now, because one digit is repeating, I'll make sure that I multiply by a number, especially like easy number I'm going to multiply with. So I'll multiply with number that has 1 0, that's 10, okay? If I'll multiply by 10 both sides, my left side becomes 10y and this side becomes 0. Because of multiplying with 10, my place value will change in a way that I'll bring the decimal to the right by one place. So when I'll do that, it becomes 3.3333. Yeah, that is the concept of multiplying by numbers like 10, 100. If you are multiplying by 100, then you move the decimal by 2 places, right? Yeah. So this is it. I have firstly multiplied by 10 both sides. And once I'm done with this, I'm going to do the same process. I'll split this number into 2 parts. This 3 is one thing and 0.333, because I can say that 3.333 is just the addition of 3 to this original number 0.333. So again, as I told you, this 0.333 is actually something I already considered as y. So I will say that this 10y is now equal to 3 plus y. Okay, now what does it give me? I'll do the same process. I'll bring this y to the other side, subtract 1y from 10y. Now you can be quick with this. 10y minus y is 9y equals to 3, giving me y equals to 3 by 9, which can be reduced because both are multiples of 3. 3 times 1 is 3, 3 times 3 is 9, so y equals to 1/3. So if you'll use your calculator to divide 1 by 3, it gives you the same number, same decimal number, 0.33333. Isn't that easy? Now note that whatever number of decimals we have, whatever number of decimal values are repeating. So let's say, for example, if I give you 0.23232323, so as a group 2, 3 is repeating. There could be possibility like this. So how to deal with this? You just look at the number that's being repeated. You have 2 digits repeating. Because you have 2 digits repeating, you will multiply both sides by the number that has 2 zeros, and the smallest number we have is 100. So I'll multiply both sides by 100. So 100y should be equal to, because of multiplying by 100, my decimal moves to the right by 2 places and therefore gives me 23.23232323, and very similar to what I had originally. Now I can say that this 23.233 can be now written as 23 plus 0.232323 and so on. Yeah. Now because I know, why did I do this, is I know this 0.2323 is y. I considered that as y, so I'm allowed to write it back as y. And what happens next? Again, y goes to the other side to get subtracted from 100y. 100 minus 1 is 99, so I'll have 99y equals to 23. So y should be equal to 23 upon 99. You can check in your calculator and see if it gives you the same decimal expansion or not. Okay, so the trick is whatever number of digits you have repeating, you will multiply by that many zeros, or I mean obviously you don't use zeros alone, so you will have to multiply by the tens place similarly, like like the 10, 100, 1000, 10,000 and so on. Okay, that is the concept of converting any sort of decimal like this. But sometimes you also have numbers like 1.2353535, only 35 is being repeated. Yeah, so what kind of number? I can write it otherwise in the bar form as 1.235 bar, only the bar is just above 3 and 5 while 2 is not being repeated. So in such cases the method of working out is a little different, because you have that non-repeated digit as well. So we will do this in the best, easiest way possible. I'll again start with considering this as some variable. I can say it as a. Yeah, let a equals to 1.235353535 and so on. Now, there are many ways these kind of questions are approached. So if you're asking me, or if I have to teach you the easiest way, I want you to have two equations here. One, where I'm going to bring this non-repeated digit once, and in the next place I'm going to bring one group of this repeated unit in front of the decimal. Okay, we'll do this in two steps. So the first step would be to remove this non-repeated digit. There is only one digit non-repeating. So I will bring this digit to the left, or in front of the decimal. To do that, obviously there is only one digit non-repeated, so I have to make sure I multiply this equation by 10. I will multiply by 10. It gives me 10a at the front, and then obviously because of multiplying by 10, the number becomes one place higher. So 1.2 will now become 12.353535. Now what do we have is we just have the repeated part after the decimal. Because I have two digits repeating, I will take this new equation, and into this new equation I'll multiply by 100. Why 100? Because I have two digits repeating. Okay. Now note that we are already multiplying with our new 100 is now multiplied with this term 10a. Yeah, we are multiplying with 10a here. So don't forget that it is supposed to be 10 times 100 now. So 10 times 100 is 1000. So what I get on the left is 1000a equals, I have to move the decimal to the right by two places, making my number much higher, 1235.35353535 and so on. Okay, now I have the two equations, this two. What do you want to do from here is, you see, after the decimal you have everything same for the two numbers that for the two equation. Now there are multiple ways again you can approach it from here, but I suggest, because we have the common decimal part, we can subtract the two equations we wrote in order to get rid of this decimal part. Okay, so what will I do is I'll subtract this lower one from the higher term. So I'm subtracting 10a from 1000a. I'm subtracting 12.3535 from 1235.3535. Okay, so you can do one thing, you can write this equation once again so that you can have the lower values at the bottom and subtract the like terms and the like decimals. The decimals are completely the same, so I can get rid of them easily. Subtracting is just take the numbers and find the difference. 1000 minus 10 is 990, so 990a equals 1235 minus 12. Remember, the decimal parts are all the same, so they will cancel out each other. Okay, because there are infinitely many 3 5s going on and on. So that is the reason why we'll cancel out completely. 1235 minus 12, please do it. 2 subtracted from 5 is 3. 1 subtracted from 3 is 2. So 1, 2, 2, 3. Okay. Now, what do I get? I have 990a equals to 1, 2, 2, 3, telling me that this a has to be equal to 1, 2, 2, 3 upon 990. Okay, because I want to remove that 990 which was multiplying other side. So my suggestion, you always oppose the operation, meaning 990 was multiplying other side, so it will come and divide other side. Now clearly, if you'll see the top value that you have, 3, 2, 2, 1, upon adding, what do you get? 3, 4, 5, 6, 7, 8, just 8, yeah? And I cannot really cancel out by 3, So obviously there is nothing I can do further because I cannot simplify the two numbers. They are already in the simplest form. They could not divide each other, or there is no common number that can reduce both of them. Okay? Hence, I will keep this fraction as it is, telling me that it has to be 1223 upon 990. Yeah? So this is how I can actually approach questions based on any sort of decimal expansion given to me. And you know, the technique is very simple. If you have some non-repeated digits, then I really suggest you go in two steps like this. Okay, you want to get rid of the non-repeated decimal first, and then you'll take the whole repeated decimal as one unit and multiply by that many zeros, or just multiply by that multiple of 10 containing exactly that many zeros. And this is how you will definitely approach questions based on decimal expansion. I'm sure this has made a lot of sense, and this is the exact kind of questions they'll ask you in your exam. Okay. Apart from this, they will give you a lot of questions like whether you should classify. You have to classify whether a number is irrational or rational. These kind of questions you have most commonly asked from this section. So I will take a lot of other examples, like for example, they'll ask me to find an irrational number between two rational numbers, or sometimes they'll give me two irrational numbers and ask me to find a rational number. So there are a lot of ways we do these kind of questions. So let's have a look and let's try some questions from exercise 1.3. Okay. In exercise 1.3, the basic kind of question they begin is to decide whether the given expansion or whether the given fraction is a terminating decimal or a non-terminating decimal. Okay, so every fraction, for example, if they ask you 329 upon 400, is this a terminating decimal or a non-terminating decimal? What kind of decimal? You have to classify it. How would you do? Now, as I showed you, the standard way that you check for this is simply by division. You divide 329 by 400. Clearly, the number is less than 400, so I'll write 0 and then I'll put decimal and then I'll put 0 here, right? Because after putting the decimal, I'm allowed, or this is the technique, after putting a decimal, we put 0, 1 at a time. So I will just compare the first number 4 with 32. I know 4 into 8 is 32. So 400 into 8 will be 3200. So upon dividing, I will get 3200, and then the remainder is just this 90. Because of the decimal I've already introduced, I'll put 10. Now 4 times how much is 9, or nearest to 9? 4 times 2 is 8. So 400 times 2 is 800. Gives me 100 as the decimal or the remainder. Another 0 if I'll put. 4 times how much is nearest to 10? So always compare. This 2 zeros will come down here, so I'll just compare the last number 4 with the remaining part 10. So 4 times how much is nearest to 10? 4 times 2 is again 8, so 800. Removing 800 from 10 gives me 200. Because of the decimal, I'll put one more 0, and now 4 times 5 is 20, thereby 400 times 5 is 2000, yeah, which is 2000. So it is definitely going to give me a remainder 0. Remainder 0 means this is terminating decimal. We'll call it as terminating decimal, and this is how you solve. Yeah, so easy actually. By just regular division, you can figure out whether some fraction, all fractions are rational numbers, but rational numbers are of two types. Either they are terminating or non-terminating repeating decimals. Okay. Whereas now they have this main classification of rational and irrational is based on this only, the expansion, the decimal expansion. If the decimal expansion is terminating, If the decimal expansion is terminating, then it is always rational, for sure, okay? Any terminating decimal is a rational number. Now, when it is non-terminating, there are two options. If it is non-terminating, then there are two options. Either it will be recurring or repeating, or else it will be non-repeating or non-recurring. Now, when it is recurring, like I showed you the example of 1/3 or maybe 1 out of 7, you can take anything like this, 3 out of 11, you will see that the digits will keep on repeating. So 0.33333 or maybe 0.179, 179, 179 and so on. Yeah. Whereas if it's non-recurring, then what is it? We really don't come across these kind of values where they are non-terminating, non-recurring. If I'll have to take an example, for example 0.010010001, though it's like a pattern, but the digits are not repeating, it's not the same group that's repeating. Yeah. This way you can be more creative in figuring out these kind of non-recurring, non-terminating numbers by yourself, okay? Similarly, if you think about finding the number that multiplies with itself to give you 2, which is now called as square root 2, okay? Square root 2 means that number which multiplies with itself to give you 2. There is no such perfect number. So, the expansion of this will keep on going, okay? It will be 1.414 and it just goes on, 286, I mean it just goes on and on, alright? So, what kind of expansions they are? They are non-terminating and non-recurring. So, this forms the different classification, or this kind of numbers are now entirely different family than what we have been studying. So, these kind of decimal expansions are now called non-terminating, non-repeating. The one word we describe them is irrational numbers. So, this is irrational. Any decimal that is non-repeating and non-terminating, that happens to be your irrational numbers. Okay, and I've showed you before, if rational is this family, then irrational will be completely outside that. Okay, this is rational and this is irrational. Now, there are infinitely many irrational numbers too. Don't think they're just finite, because you can go ahead and think as many irrational numbers possible. There are 0.35, 355, 3555. You know, you can just be creative and just go on with different kind of patterns to find these irrational numbers, and yes, they will exist. So, this is the entire family of numbers. Okay, this is the total entire family of numbers, and the whole family is now called the real number system or real numbers. Now, these irrational numbers, as I said, they are easy to find. So, what they'll ask you is, they'll give you two numbers, like they'll give you, they might ask you find between 2 and 3, can you find an irrational number? If you have to find irrational number between 2 and 3, then what can you do? Just think of whatever is coming in your mind. Just make sure that the decimal part is non-repeating, non-terminating for sure, but non-repeating as well. So, 2 and 3, between 2 and 3 lies 2 point something. So, 2.12, 122, 1222, anything, it goes on and on. Okay. Similarly, you can write down 2.01001, 0001 and so on. So, this is how you just become creative again. Okay, just see what kind of digits you can form, and just take any random digits, but you know, you have to show that it is never repeating. All right, And if they'll ask you a fraction, like they'll ask you 5 by 7 and 9 by 11. This is a question from your exercise again. So 5 by 7 and 9 by 11, if you have to find 3 irrational numbers between them, what will you do? 5 by 7 is a kind of decimal. You can just divide 5 by 7 and find out the decimal expansion of this. Similarly, we'll do the same thing for this one. 11 will divide 9. Okay. If 7 divides 5, then you can try 7, obviously 0.50. So 7 into 7 is 49. 51 is the remainder. 10 it becomes. 7 times 1 is 7. Remainder is 3. 30 it becomes now. 7 times 4 is 28. 2 is the remainder. 20. 7 times 2 is 14. Gives me 6 as the remainder. 60 now. 7 times 8 is 56. It gives me 4 as the remainder. 40. 7 times 5 is 35. Now it gives me the same digit that I started with, 5. So it will become 50 now, right? 50 is what I started with. So upon getting 50, you know 7 times 7 is 49. So this whole group will repeat. All right. This one, 9 upon 11. 11 divides 9. Obviously not divisible. So I'll put 0 point and then make it 90. 11 times 8 is 88. 20. Yeah. 11 times 1 is 11. Giving me 9. So 90 again. So 11 times 8. You can clearly see it's just 0.81 because I'm going to get another 8 then followed by 1, 8, 1, 8, 1. It will keep on repeating. So we got the number 0.714285 and the other number we got is 0.818181 repeated. They ask you to find 3 irrational numbers in between these two. How will you do? You can take anything. So between 71 and 81, you can take anything. So 72, yeah, 0.723, 223, 223, and so on. Okay. Similarly, 0.75, 775, 775, and so on. You can go ahead and write down 0.79, 799, 7999, and so on. So yes, you can just form as many as you can. They're just asking for 3. So, you know, this is how exactly you find irrational numbers provided you have been given 2 rational numbers. So this is the exact kind of questions you have in your exercise. And apart from this, they'll ask you to classify numbers whether they are rational or irrational. So sometimes they'll ask you square root of 23. Is that rational or irrational? Clearly, you have never seen 23 occurring in the table of any number. So it's a prime number. So one important thing I can share as a prior knowledge would be the square root of any prime number you consider. Okay, the square root of any prime number you consider, because prime numbers do not have any kind of factor. You cannot imagine them to have some perfect square root value. So square root of 23, there is no number that multiplies with itself to give you 23. Like there is no perfect number. Obviously there is some irrational value, or there is that kind of weird decimal value that will exist. Okay, so if I'll have to tell you where will it lie between, you know, square root of 25, yeah, 25 square root is 5. So it's very clear that this number will be very close to 5. Okay, it will be 4 point something. You can just estimate like that, but you really cannot tell what exact value it would be. Yes, hi, good afternoon. I hope you will understand this with what I'm teaching. I want this topic to be very easy for all of you, for all class 9 students. When I did my class 9, I remember doing it and I quite did not like it initially, you know. So I'm trying my best to make things easy for you so that scoring from this topic is just very simple. And once you have understood this now, it becomes very convenient in class 10 and further as well. I mean, if you are going to give many exams further, then I want you to, you know, understand these basic things, because they will test you on something similar, okay, or the concept that is connected to these things only. So as I was saying, square root of 23 is a prime number, so all square root of prime numbers, they are irrational. Okay. Now, they might ask you to, you know, twist things, and they'll ask you, what if the square root of 225 is given to you? Now 225, because it's ending with 5, you want to test out if this number is a square number. Now I usually suggest my students, you know, it's very helpful when you remember or when you learn and try to memorize the first 20 square numbers. You know, square numbers are very handy. So 225, does it appear in the square, or is it a square number? Does it appear as a square of some perfect numbers? To find it out, of course, I mean, there is a method you can find it out, and that is done by the usual branching out method. That is something we have been commonly doing in our previous classes. Yeah, in our class 6, 7, 8, you do this. So 225, because it's ending with 5, and at the same time I know that you know, the sum of digits 5 plus 2 plus 2 is 9. So it's divisible by both 3 and 5. It's very clear to me. So I can go ahead and start with 5. Okay, 5 times how much is 22, or nearest to 22? 5 times 4 is 20, and 5 times 5 is 25. Now 45 is again divisible by 5. 5 times 9 is 45. 9 is something I can write it as 3 times 3. So instead of 225, I can go ahead and write the prime factors. I'll write them in powers. So 5 squared and 3 squared. Now square and square root, the words, I mean, they are connected, yeah? Square, square roots. The roots are nothing but the opposites of the respective power. So square and square roots are reciprocals. They will cancel each other out. Like plus 3 minus 3, that gives you 0. Like 3 times 1/3 gives you 1. Yeah, I mean, these are some examples of inverse values, or, you know, inverse operation. So dividing by 3 and multiplying by 3 does not affect the result, isn't it? Similarly, square and square root, they always cancel out, giving you what you have inside is just 3 times 5, 15. So yes, the square root of 225 is a rational number, 15. 15 is a rational number, so square root 225 is a rational number. Don't say it's irrational just because it's inside the root. Okay? If you have perfect square numbers inside the square root, or if you have perfect cube numbers inside the cube root, sometimes they'll ask you if cube root of 8 is a rational value or an irrational value. Then the answer is, I have to write down 8. I have to prime factorize 8 again. So branching out 8 gives me 4 times 2, and 4 can be written as 2 times 2. So upon prime factorizing 8, I get how many 2's? 1, 2, 3. I got 3 2's. So if I have 3 2's, then I can write this as, instead of 8, I'm going to write 2 to the power of 3 cube root. As I told you right now, roots and cube roots, or the roots and the particular square, or sorry, the particular power, they are always opposites. So they cancel out. Cube root of 3 is 2, which means it's a rational number now. So this is the concept of identifying rationals and irrationals. If you have the root of some number, like square root of 6, if somebody would ask you, square root 6, is that rational? No. Why? Because 6 is written as 2 times 3, and technically I don't know a perfect number, or obviously upon taking the square root of 2 and square root of 3, both are irrational values that will give me the infinitely going, non-repetitive, non-terminating decimal. So they are both irrational values. So logically 6 is not a square number. So because 6 is not a square number and there does not exist a particular number that multiplies with itself to give you that 6, so it is irrational. Okay, so this is the concept of identifying irrationals and rationals. This is what you have in section 1.3. Section 1.3 is done, and the next part will be all about understanding the properties of irrational numbers and operating with them, which is something I like and I hope you will enjoy. That's it for this lesson. I will see you in the coming one.